In this video, we're going to look at how to determine the rate law by using the elementary reactions. So of course, kinetics and rate laws can be used to determine a reaction mechanism. Just to review, reaction mechanism, of course, is a sequence of smaller reactions that describe the pathway that get us from the reactants to the products. The elementary reaction or elementary step is a single step in a reaction mechanism. So if we look here we have the overall balanced equation, and this particular overall reaction is comprised of two elementary steps. So in order for this reaction to occur, it must go through these two elementary steps. Remember that the overall reaction is just a summary of the elementary steps, or the sum of the elementary steps. Now, in regards to rates, each elementary reaction is a chemical reaction, so each elementary reaction occurs at a different rate. Therefore, each elementary reaction has its own rate law and its own rate constant. So each of these elementary reactions occurs at a different rate, and so each one will have its own its own rate law and its own rate constant. So here, this would be the rate constant for this elementary step, and this would be the rate constant for the second elementary step, K1 and K2. Since this is the first one, this is the second. If we had a third, the rate constant we would call K3. Now, as we mentioned, each elementary reaction occurs at a different rate. One elementary reaction may be slower than another. How can you tell by looking which one's slower? You can't. You have to be given that information. And here we're told that the first elementary reaction is the slower reaction and the second one is faster. The slower elementary reaction is what we call the rate determining step or rate determining reaction. Essentially, it acts as a bottleneck which limits the rate of the overall reaction. You can kind of see this analogy here. The water flows through the smaller funnel at a slower rate, and so the rate at which the flask fills is determined by the rate at which the water flows through the smaller funnel. It could be the first step, it could be the second step, it could be the third step. But essentially, each of these could be thought of as an elementary reaction. Whichever reaction is the slowest determines the rate of the overall reaction. That's very important. Let me repeat that. The rate, whichever elementary reaction occurs at the slowest rate, that rate is the same as the rate for the overall reaction. It determines the rate for the overall reaction. Now we could also graph this using a free energy diagram where here's my reactants, here's my products, and again this occurs in two steps, so we have some intermediate here. The first step in our example was the slower step, and so it has a greater activation energy than the second. So we could graph that as you can see here. So let's get back to our example. Here we have a reaction mechanism. The first elementary reaction is the slower and the second is faster. Now, since an elementary reaction is an individual molecular event, this is important, since the elementary reactions are individual molecular events, the order of each reactant, and therefore the order for each reactant in the rate law, can be determined by the stoichiometry of that elementary reaction. Now that's not true if we're just looking at an overall reaction, because it's not an individual molecular event. However, we can write the rate law for an elementary reaction and determine the order by looking at the stoichiometry. So if I wanted to figure out the rate law for this overall reaction, I would look at the slower step, the rate determining step, and I would write a rate law using the elementary step that is the slowest one. So here, I could write the rate law for this reaction. The rate is equal to K1, that's the rate constant for that reaction, times the concentration of my reactants. Here we have NO2 and we have 2 moles of that. So it would be NO2 squared. Now we can't do that again if we're just looking at an overall reaction, but we can get the order, in this case second order with respect to NO2, from an elementary step. That's very important for you to appreciate. Now let's look at another reaction mechanism. But in this reaction, the rate determining step is the second step. So here, let's say we had these 2 elementary reactions. This is our reaction mechanism. And the first one was fast, and let's say it reached equilibrium. And the second was the slower step. So because the second is slower, the first, we can assume the first reaction is going to reach a state of equilibrium while it's waiting for the second reaction to finish. So before we talk about this, pause the video and see if you can write the overall reaction for this chemical mechanism. Okay. So if I add these 2 reactions together, this is what I get for my overall reaction. Now, how would I write the rate law? Well, first, I would look at the slowest step, in this case, this one, and the rate is going to be equal to my rate constant K2 times the concentration of my reactants. So it would look like this. Based on the slowest step, the rate is equal to K2 times the concentration of N2O2 times the concentration of Br2. So that is the rate law. But there is a problem. If you notice, here in our rate law, we have an intermediate. N2O2 is not one of the reactants in our overall reaction. And according to our rate laws, we cannot have intermediates in our rate law. So we have to do a little bit of a rearrangement, a little bit of trickery here in order to get rid of this intermediate. So let's look at the steps on how we can write the rate law in order to get rid of the intermediate and express it in terms of the reactants here. Okay. So the first step is to write the rate law for the forward and reverse elementary reaction occurring immediately before the rate determining step. So if I look back here, here is my my elementary reaction that occurs immediately before the rate determining step. And so I want to write the rate law for the forward reaction and for the reverse reaction. Okay, because again, we're assuming something called the steady state equilibrium. We're assuming that since this is my slowest rate determining step, that all the reactions above that are going to be at equilibrium. And that's generally a good assumption. So let's write the rate law for the forward and reverse reactions. It should look something like this. The forward reaction, rate is equal to K1 times the concentration of NO squared. The reverse reaction also has a rate constant. We call it K minus 1 because it's the reverse of the first one. So the reverse reaction, the rate is equal to K minus 1 times the concentration of N2O2. So for the reverse reaction, this is my reactant. For the forward reaction, these are my reactants. Okay? So follow along here now. We have these 2 rate laws. Let's go on to the second step. Since we're assuming that first step is at equilibrium, then the rate of the forward and reverse reactions must be equal to each other. So we can set those 2 reactions equal to each other, those 2 rate laws equal to each other. So here is the rate for the forward and the reverse. Let's set them equal to each other, and we should get something that looks like this. So I've just set these 2 equal. Now let's move on to the third step. Now we have to solve algebraically, if you will, so that we get rid of that intermediate, or we isolate the intermediate that we're trying to get rid of. So here, again, here's my intermediate that I'm trying to get rid of. I want to isolate that on one side. So I'm going to divide both sides by K minus 1. So if I divide both sides by K minus 1, my K minus 1s cancel here, and I end up with concentration of N2O2 is equal to all of this. There we have it. Now we're not done yet. Follow along. We got a couple more steps. Next, we have to substitute this new expression, the one we just got, back into our original rate law for the rate determining step in place of the intermediate. So again, here's what we just solved for. So the concentration of N2O2 is essentially equal to this. Now look back at your original rate law. Remember, we're trying to get rid of this intermediate right here. So we want to replace that intermediate with what we've just solved for here. So we're just expressing, we're not doing anything really crazy. We're just expressing the concentration of the intermediate in different terms. So if I put that in here, I get an expression that looks like this. Rate is equal to K2, and this is what used to be the concentration of that intermediate times Br2. Now what I'm going to do is just rearrange it a little bit. I'm going to group all of my rate constants together. And so I have my rate is equal to this ratio of my rate constants times the concentration of NO2 squared times Br2. Now I've written the rate law in terms of the reactants from my overall equation. Now I can combine these rate laws into one and just call it K. Okay? So the rate is equal to K times concentration of NO2 squared times the concentration of Br2. So again, this is obviously a little bit trickier, but the key there, what we're trying to do, we write the rate law from the rate determining step, just like we would before. We just have to do a little bit of trickery, if you will, to get rid of an intermediate and express it in the proper terms. Now, if you do that step and there's still an intermediate, which there wasn't in our example, but if there was, then you would repeat steps 1 through 4 until, again, you got rid of that intermediate. So you would look at the reaction above the one you just did and set those two rate laws equal to each other. Okay. So let's take a look at another problem. Write the rate law for the overall chemical reaction given the following mechanism. Okay. So given this mechanism, write the overall reaction and then write the rate law in terms where there are no intermediates. So pause the video, go back and look at those steps we just reviewed and see if you can get this one. Okay, so first thing, let's add these two reactions together in order to get our overall reaction. Okay. Our intermediate in this case is NO3. Now that we've done that, let's look at our slowest step. This is my rate determining step. And now I'm going to write a rate law based on this slowest step. So the rate is going to be equal, the rate law for the RDS rate determining step, the rate is equal to K2 times the concentration of these reactants. Again, we can use the stoichiometry here to determine the order. So the rate is equal to K2 times concentration NO3 to the first order times the concentration of NO to the first order. Okay. So that's our rate law. Let's see if we have an intermediate there. Well, yes, we do. We have NO3, which does not appear in our overall equation. So we got to get rid of that. So let's follow those steps. Let's look at this reaction, the one above it, assume it's at equilibrium, and let's write the rate law for the forward and reverse reactions. Okay. So here's my rate law, and here's my intermediate I'm trying to get rid of. I write step 1, write the rate law for the forward and reverse reactions for the elementary reaction immediately above our rate determining step. Next, I'm going to set these two equal to each other. Now I just have to isolate my intermediate. So I'm going to divide both sides by k to the minus 1. Now I've got my intermediate isolated. My intermediate concentration is equal to this. So I'm going to substitute this whole thing back up here for that intermediate. Okay, I'm going to keep K2 and NO, but I'm going to replace that in there. Okay. So now I've substituted that. Now I just want to simplify my expression a little bit. I've got NO and NO, so it's going to be NO squared times concentration of NO2, and then combine all my rate constants here. Okay. So now I've just combine my NOs, that'd be NO squared, and my rate constant K, where K is equal to K2 times K1 divided by K minus 1. Okay. So again, this is a little bit tricky, but be sure you are familiar with these steps and appreciate when we need to write a revised rate law. Again, if you see an intermediate in your rate law, you have to go through these steps in order to get rid of it. So practice some of these and be sure you're comfortable doing this type of problem.